Hello. So in this video, we're going to be tackling the derivative of exponentials. So in particular, we want to sort of algebraically derive what the derivative of functions of the form of a to the x would be. So we were after this one of those general rules like we have for polynomials. In particular, this only makes sense for strictly positive a. If you have negative, right, if you have a negative base, it's flipping around everywhere. Calculus does not like that at all. So it only really applies to strictly positive versions. But we're going to sort of spend some special attention on this particular base of e. So we're going to actually start out by looking at e to the x. And it turns out that there's a pretty good reason for that, which we'll see. Okay. So as usual, sort of a first natural step to do is to look at that difference quotient, the actual sort of technical definition of a derivative, which looks like this, right? So we have that f of x plus delta x, so it's e to the x plus delta x minus e to the x all over delta x as delta x goes to 0. What do we do with this, right? This thing's kind of a mess. So turns out this is not going to be sort of solved by one of our add 0 cleverly or multiply by 1 cleverly. There's more, or sort of importantly, a different sort of technique we have to go through. And the reason is that sort of our underlying problem here is that there's really a hidden limit we're not addressing yet, okay? And that has to do with e. So as mentioned, e is sort of going to be playing a special role. So it's sort of important and noteworthy to sort of talk about e for just a second here. So it does have a very special property in calculus, which we'll show sort of by the end, and in fact, we'll get its own sort of additional video. But probably, depending on sort of your pre-calculus class, you sort of know of e at best as this sort of irrational constant, like 2.7182818 ... on forever, never repeats. It's a number like pi, sort of in your head, I'm guessing. But the reality is that e is actually a value of a limit, right? If you actually look up sort of how it came about and sort of exactly how it's defined, in most cases, and there's a mathematical asterisk there, depending on sort of which mathematician you're going to talk to, but that's a whole rabbit hole you don't want to run down. Most cases, e is literally defined as this limit. So Jacob Bernoulli is the guy who sort of went looking to figure out what is the value of this limit. This, as n goes to infinity, we have 1 plus 1 over n all to the n. And sort of, if you remember from sort of indeterminate forms back when we did limits, we were sort of talking about how you have that tension depending on what you're looking at. And here, we have something that is going to 1, right? Because 1 plus 1 over something going infinitely large, this term is going to 0, so this overall thing is going to 1. So it's trying to be small, but we're raising to an infinitely large power, which is trying to make it big. So we have that tension, so this is an indeterminate form. That's why Bernoulli sort of went through a lot of effort, because he didn't have a lot of the mechanics we have now, to actually come up with what this should be, and he named it this e as the sort of reference letter. Okay. Importantly, the takeaway here is that e is really a limit in disguise. So when we looked at our difference quotient, we had e's everywhere. So we're really taking limits of sums of limits, and like weird things were happening. And this is sort of why it was difficult to tackle. Now, instead of trying to manipulate the difference quotient directly, what we're going to do is a little manipulation on the definition of e, by which I'm not saying we're going to change the definition of e. I wish I had that kind of power, make my life as a mathematician much easier. But what we're going to do is sort of rewrite the form that we sort of associate it with. We're going to rewrite the visual of it. And to do that, we're going to substitute in, instead of things like 1 over n in the definition of e, I'm going to write it as delta x. This also means that if I have an n, right, if I multiply both sides by n and divide by delta x, n is 1 over delta x. So these are, I'm sort of defining delta x as being that thing for a second. And I'm going to notice that as n gets infinitely large, right, as n goes to infinity, remember this notation, then 1 over n goes to 0, but that means that my delta x, which is 1 over n, is going to 0, right? So this means that for my definition of E, if n is going to infinity, that's equivalent to 1 over n going to 0 or delta x going to 0, right? I still have the 1. That's just hanging out. Then plus 1 over n, I'm writing delta x as 1 over n. So I have 1 plus delta x. And then the power n, I'd have to solve for n up here, which I mentioned earlier, is 1 over delta x. So the power becomes 1 over delta x. Okay? So everything I've done here, perfectly fine. I haven't fundamentally changed the value of the limit in any way. I was very consistent. But a natural question is why? Why do this, right? Always a good question to ask. And again, the sort of unsatisfying answer is because it works. But let's see what happens when I do this, okay? So starting with the difference quotient, right? I have the limit delta x goes to 0 of e to the x plus delta x minus e to the x all over delta x. Now I'm still taking the limit as delta x goes to 0. So this is why in the sort of previous bit, I wanted the limit as delta x goes to 0 for my definition of E. Like, it's important that I was consistent there. So for the very first step, I'm just going to separate these terms, right? I'm going to look at e to the x, right? This is e to the x plus delta x. I'm going to split that up, right? So a sum in the powers is just multiplying the bases with the two different powers. Then I'm going to factor out that common e to the x, right? So I have an e to the x out here and here, so I factored out getting e to the delta x and minus 1. And importantly, that e to the x doesn't depend on delta x, right? It's just e to the x, not e to the delta x. So that means from the limit perspective, right, from the perspective of that limit, e to the x is just a constant. It's not changing based on what the limit cares about, that delta x. So I can pull it out, which is what I've done here, right? So I've pulled out the e to the x. Now is when I'm going to bring in that definition of E that I talked about. And it's worth sort of taking a second to see how I knew this was going to help, because there's sort of a lot happening here. Again, this limit was always using delta x going to 0, so it was actually really important that when I introduced a delta x for my definition of E, I actually had that delta x was also going to 0. Otherwise, I would still have two different limits here doing crazy things. So those needed to be the same in order to do what I just did. But one nice thing is that it had this 1 over delta x power in the definition of E, but I knew I was going to have a delta x power when I replaced, right, that E to the delta x. So my idea was that this delta x and this 1 over delta x, I wanted those to cancel out, so I didn't have a power to worry about anymore. So this is why I was sort of after that 1 over delta x as a power in the first place. And then the hope is basically everything else will work itself out. But that was the key piece that I was after. Okay, so let's see how that works in practice. So having a power of a power, right, that multiplies them together. But that's just delta x divided by delta x, so that goes away. Then I just have, right, so these go away. Then I still have my minus 1, and I still have my 1 plus delta x, but that's 1 plus delta x minus 1. The 1s will cancel. So then I have just delta x over delta x. Now, I still can't evaluate my limit because that would give me 0 over 0, which is indeterminate. But I could simplify, right? I could simplify away those delta x's. Now I'm taking the limit of 1, which is really about as simple as a limit could get. Maybe limit of 0. But like, can't really ask for better than that, right? So as delta x goes to 0, the limit of 1 just stays itself. So I can evaluate that limit, and I just get e to the x. So all that annoying algebra to get e to the x. But wait, hopefully, I'm hoping this is setting off a thing in your head, Pavlovian reflex maybe, but I'm hoping you notice we just showed that the derivative of e to the x is e to the x. So this is sort of surprising, right? Like every other derivative we've taken has changed the output, right? When we did x to the n, we got n x to the n minus 1. It changed the degree of the polynomial. When we do, all of our pieces, right, when we do our sums and things, they all break apart, and they break apart into new things. Here, we did a derivative, and it did nothing. So it turns out this is surprisingly important, and this is the special property, the thing about E that is so interesting from a mathematical standpoint. I realize maybe not so much from a student standpoint, but useful. That's something for a student. So we'll see a separate video, actually a couple of them, on why that's so useful in a separate videos as well. All right, so we've done e to the x, great. But remember, our original goal was to do a to the x for some a. So to be very explicitly clear here, a is a constant. It's not a variable, meaning that I want to be able to take a derivative of 3 to the x, 7 to the x, pi to the x, e to the x. But this is not the same, I want to really emphasize, not the same as doing something like x to the x. That's a whole different bag of pain, really. So not that. It is some explicit number. We just don't know what that is. That's why we're using E. That's why we're using a here. Okay. All right. Now we could go down the same rabbit hole, do a difference quotient, all of that stuff. But rather than going that way, there's an easier path, much easier path, it turns out. And we can do that by manipulating our expression a to the x before we take a derivative. And in fact, what we're going to use is some properties of exponentials and logs. So in particular, we're going to use the property that e to the natural log of something is just that something, right? The e and natural log cancel each other out. That's the whole point. We're also going to use the fact that natural log of a to the x is x times natural log of a. Again, very important here that a is a constant, right? Because we haven't actually discussed how to deal with natural logs from a derivative standpoint yet. But natural log of a isn't sort of natural log as a function because a isn't changing. So I can think of natural log of a as being a number, meaning if a is 17, this is just the natural log of 17. It might be a gross number. Natural log of 17 is not great, but it's still a number, right? And as we've seen, constant multiples, right? Constants, when I multiply by them, can go in and out of derivatives. All right. So using those two properties, I can rewrite a to the x as, right? So I have a thing. I can write it as e to the natural log of that thing because the e and natural log cancel, right? So those are equal. That's my first property. And then I can use the second property to pull out that x, right? Natural log of a to the x is x natural log of a. So I can rewrite a to the x as e to the x times natural log of a. Okay. Now let's go through the actual derivative. So taking derivative of a to the x, that's equivalent to taking the derivative of e to the x times natural log of a. That's the identity we just did. This is also, by the way, a key reason why we need a to be strictly positive is because we want to look at natural log of a, and natural log is only defined for strictly positives. So this is why sort of trying to do a negative, I said calculus doesn't play nicely. That is drastically underselling that point. You need a whole sort of post-advanced calculus class, usually complex analysis, to do that. It's a whole thing. We're not going to do that. Don't worry about it in this class. But it is important that a is positive. Okay, so that bit aside, continuing. So taking the derivative of this thing, well, we know what the derivative of e to stuff is. It's itself, e to stuff, right? We just showed that. E to the x's derivative is e to the x, but we still have this chain rule bit, right? So the derivative of the thing of e to something is itself times the derivative of that something, okay? So this thing didn't change, but I did pick up that additional chain rule. But that chain rule is pretty straightforward because, again, beating on a dead horse here, but natural log of a is a number. It's not a variable, right? A is a number. So this is really something like 3x, meaning that the derivative is just pulling out that constant multiple, that natural log of a, and then taking the derivative of x, which, again, the letters match, right? So the derivative with respect to x of x is just 1, meaning that I have 1 times natural log of a, or just natural log of a. So that's what this is, okay? And finally, I sort of, should probably put this back into the right form, right? So e to the x times natural log of a, that was really another way of writing a to the x. So I'm going to simplify it by replacing that definition back again, right? Instead of having this crazy looking e to the x times natural log of a, I'm just going to rewrite it as a to the x. So as a sort of end result, what I'm showing is that if I need to take the derivative of something to the x, it is itself times natural log of that base, right? But there's a little bit more I want to sort of take away from this, because we've sort of shown now two rules, and sort of noteworthy is that these things are usually taught as two rules, and students usually try to memorize these things as two rules. And the reason I'm a mathematician is that I have a terrible memory. So whenever possible, I want to show that there's really less to memorize than you might think. I might make the argument that, learning is better than memorizing, but I realize my crowd. So I will at least do this much, which is we can actually use that e to the x rule. Like we used it to get a general a to the x rule for any a, but importantly, that counts for the a value that is e, meaning like this works for any a that is positive. It works when a equals e. So if I try this with a being e, meaning that if I try this with a base of e but use that a to the x formula, right, I would get derivative of e to the x is natural log of e times e to the x, right? Derivative of a to the x is natural log of that base, natural log of e, and then itself, that base to the x, e to the x. But natural log of e is just 1, right? That's the whole point of natural log. E to what power is e? 1. And that gets me back to e to the x. So this tells me that I don't really need to think of these as separate things. This is the same formula. It's just that it's nicer when the base is e, because I don't have that extra natural log term. But if I were to write it using that general a to the x formula, it still works. There's not really two rules to remember here. There's really just the one, okay? As a footnote, a lot of people, for whatever reason, sort of worry about 1 in particular, and 1 still works as well. So this is more just in case this comes up, because for whatever reason, in my experience, this comes up a lot as a question. If you were to do this with 1 to the x, it still works, at least for real numbers, which again is all we're worried about in this class. But that's because 1 to any real power is 1. So really it's a constant, and the derivative of a constant is going to be 0. But nonetheless, if we go through the formula, right, we're going to have natural log of that base times whatever the original was. I guess that should be a 1, sorry. But natural log of 1 is still 0, right? So I get 0 times whatever it is, which doesn't matter because the 0 annihilates it. Literally call it the annihilator in mathematics. So 0 annihilates it, we get 0 just like we should. So if this is a question you have or comes up for whatever reason, yes, it works for 1 as well. All right. So what do we do? So there's sort of two bits here. One is that we sort of stumbled upon, perhaps even accidentally, that there's something special going on with e that makes the derivative of e a very sort of different process, but also a very nice process, right? Like taking that derivative of e to the x got us e to the x. We saw that something sort of didn't happen in some sense, which was surprising. But nonetheless, sort of taking that process, we could immediately generalize it to any positive base, right? We did it initially for e, this irrational, crazy number, but it immediately worked for all bases that were positive. And so we got these two sort of rules, which again, I want to really stress is really just one rule, but we got these two rules. The derivative of e to the x is itself, and for any base a to the x, we can just do natural log of that base times a to the x, which again, I know beating a dead horse here, but if we plug in e as that base, this becomes 1 times e to the x, which is just e to the x. So really the only formula you really sort of need as a takeaway is this last one, okay? All right, so that is that.